purpose, each repair on aircraft structure has to be able to sustain the original justified design load. So you can see the word here, sustain. Sustain original justified design load. For static, fatigue, damage tolerant requirement. Okay, means that sustain original. So that's why we define repair as restore. Repair is defined as restore because we want it to sustain the original justified design load. So we repair the structure to restore the design, the strength capability. In most cases, only the static requirement need to be met for the repair principle on secondary structure. So for secondary structure, only work on repair on the static. For fatigue and damage tolerant is not required to be justified because fatigue and damage tolerant require first more competent person to do. Second, require more data because to do fatigue and damage tolerant analysis, you need to have the aircraft flight spectrum data. From the flight spectrum data, we can analyze what will be the inspection interval for the critical crack growth. First, you have to identify what is a critical crack growth, and then you have to look for these stresses on the area, and then you have to look at how the aircraft fly using the flight spectrum, and then from there you will be able to crunching the number to determine what would be the inspection interval of the aircraft structure. So normally, that's why if you work for the airline later on, you use this document to design the repair, and then you send it to the Airbus, and Airbus will come back to you, say if your design is good, they will say yeah, the repair is acceptable, or if not, they will comment on it and they say do the repair after you do the amendment as per what they required. And then they say for damage tolerant analysis, you have to wait for a few weeks. They will come back to you. So when they come back to you, they will come back to you with an inspection interval for the repair that you designed when you need to do the inspection. So those are the result of a fatigue and damage tolerant analysis, where you can get the inspection interval for the repair. A static or stress analysis is performed to make sure the structure can withstand the applied ultimate load without failure, without permanent deformation at the limit load. So first, you are required to do static stress analysis. Okay. So that's why you cannot run away from. That's why I'm trying to teach you to give as much information for you to be able to have the skill or the competency to do the static stress analysis, because that is required. In fact, this is the written and the manual. You have to do static or stress analysis. So that is what the knowledge that I'm trying to impart on you, for you to be able to do this static stress analysis. There are two main approaches in demonstrating the static strength. Okay, there are two ways to do. Okay, first, okay, just go straight to the second one. This is what reverse engineering. Most of the time we do reverse engineering. That's the second method. First method, you have access to OEM, and you have all the information on the load that going through each structure. Then you are doing the first approach. So meaning detail of the applied load are known. detail of the applied loads are known. You know how many Newton that go through for each member, the skin, the stiffness, the bulkhead, the frame, in fact every fastener also you know the load. So loading unknown. In this case, detailed stress analysis of the part to be repaired result in optimized repair design. So because you know the load, you're not guessing, you know exactly what goes into that, then that is, and then end up your repair will be optimized. And then generally, this is the approach is taken by the manufacturer. You are at the level of manufacturer, because manufacturer will have, they call it stress manual, and that stress manual will give all the detail about this of each structure, loads and stress and factor of safety, margin safety. When I was working for the C130 for airrod, we do have this stress manual, and easier for us because every time the aircraft damaged, we just go to manual, we refer to the part that has been damaged. We know exactly what part is used for, what kind of load go into that, how much tension, how much shear, how much bending, torsion, and also to the detail what is the factor of safety for that component, for each part. So easier for us. Some factor of safety is high, and then if they have some minor damage, for example, some corrosion, light corrosion, and then we go back and look at the factor of safety is still higher than 1.5, we can just let go the aircraft use as is. So that's the beauty of having this stress manual. And most of the time, no detail of the applied load. No detail of the applied load. We do not know. We just look at the aircraft, we just look at the structure. We have no idea what will be the load that going through the structure. That is happen all the time when we operate the aircraft, when we own the aircraft. We were not OEM. We do not have any access to OEM. OEM will give you access to structure repair manual, but they don't give you access to the stress manual. Unless you're a very big airline, for example, big airline in the US, American airline, or whatever airline that is big with thousands of aircraft, and then they may have access. The OEM will share those information because they got too many people to handle, so they let the airline to work on themselves and they give the information. So we do reverse engineering. We do not have the load, then we have to do reverse engineering. We will talk about it later. Scope and limitation. Okay, for this manual, this topic presents some guidelines which may use when designing repair for extruded and form section. The guidelines are based on the reverse engineering method. So here also will explain to you how to do the repair on extrusion or form section, and not just a skin section, complete. And remember again, as we learn, the aircraft structure is very simple. Either you have skin or either we have angle. The skin angle put together, they can become spar, they can become frame, they can become bulkhead. So that's how simple the concept. So the structure design also, the structure repair design also can be very simple. Either the doubler, patch for the skin, and splice doubler for the extrusion and the form section. And then you mentioned again, the repair is to restore, restoration of static strength. Okay, the resulting repair will be therefore comply with the static strength requirement. This guideline, when used together with other standard design principle and guideline, fastener hole, drill data, spacing, margin, sealing, may be used repair to secondary structure without referring back to Airbus. So you use this guideline, and then you couple with other manual, okay, on each work, drilling, installing fastener hole, margins of safety, margin data, sealing, all the detail you follow. So this guideline plus that information, you put them together as the engineering order to repair, and that one can be approved without on secondary structure, remember, on secondary structure without going back to Airbus. In Malaysia, the CA will give you an approval to do this. You will be Part 21 Sub Part J, Design Organization Approval, and you have this approval to approve your own repair, design or repair on secondary structure. So you don't have to go back to CM. You don't need to go and wait for them until they send out that repair approval. And then this guideline also used when designing repair which are to be submitted to Airbus. Like I say again, if you want to submit to Airbus, for them to assess this your repair, for them to be able to review the repair easily, because you already use the principle that they have put in, then you will have less time for them to approve your repair proposal. Okay, any question?
So far no, sir.
Okay. Okay, even though they are not focused on fatigue and damage tolerance, more focused on static. However, the general guideline of cutting, drilling, machining, all those methodology for you to make the doublers, to make the fillers, to cut the damage area, you have to follow this manual. This manual will already have built-in damage, fatigue and damage tolerance principle in that kind of activity. So that's why we have shot pinning, we have heat treatment, we have hydrogen embrittlement. Those are one of the elements for you not to fail prematurely because of fatigue and damage tolerance. Because of fatigue, yeah. And then next you can see the list of symbols. So this is engineering properties, material values. We have to see here FBRU, FST, FSU, FTU, FSTY. So this is something you always see when you do mechanical material. So this appear again. Like I said, you cannot forget them. They will see this again in this manual. So whoever now, I think it's too late for you. Whoever now doing mechanical material, hopefully you'll be motivated by seeing this because this is one appear, whatever you do actually appear in the aircraft manual. And then there's a term here, factor of safety. We have reserve factor, we have margin of safety. So this is a term. Factor of safety is purely for the certification. Any primary structure should have 1.5 margin of safety, meaning 50% extra in terms of strength. So you design something to 150 Newton, you only apply 100 Newton, so you have 50 Newton extra margin. So that margin will be able to handle anything, errors, environmental issues, or any structure overload, unexpected operational load, things like that. Then there's another term, we call it reserve factor. Reserve factor, you just divide by allowable load to the allowable load to the applied load. So allowable load you design to say 150, allowable load is 100, so you have reserve factor more than one. So you may only work on a primary structure to require 1.5. For secondary structure, fairing is something not critical. You may use less than 1.5. So if you you apply allowable load you design to 110, you apply at 100, so 110 over 100 you got 1.1. So it's more than 1, so it's acceptable. Should not be less than 1. That is reserve factor. Means you still have some reserve load in the structure. Margin of safety is a reserve factor minus 1. Should be more than 0. So say you have 110 as allowable load, apply at 100, you got 1.1. You minus 1, you got 0.1, so still okay because it's positive. It's higher than 0. So it's three terms always been used. And first term is regulatory term. So this is used when you want to do certification. You must have the Factor 1.5 for especially for the primary structure. Okay. Any questions so far?
Okay, sir.
Okay, next material, repair material and dimension. In order to restore, remember, repair, restore. A basic principle when reinforcing and splicing is to use the same, remember, same material as the original. First rule. So if your original material is 2024 T3, your doubler should be 2024 T3. Okay. General principle. If you are unable to get the doubler, you go back to the manual, you look for substitution. What can you substitute? What are the materials to substitute 2024 T3? If not there, and then you have to use ready engineering, and then you have to justify. If you have everything in the table from the manual, you don't have to justify. You just refer to the manual. If not, then you have to justify yourself. The worst, you may need to require to do the testing. So that's why most of the time we just follow the manual. We just follow what are the allowable substitutions, so easier for us. So same material. Yeah. Then thickness of the repair part shall ensure the cross-section area of the repair restore the original cross-section area. Okay. Shall be ensured. Generally used. Okay, what thickness will be? 1 gauge thicker than the original. 1 gauge thicker mean if the original is 1, you go look at the table, 1 gauge thicker is 0.2. If your original is 1.4, you can look at the table says the next thickness you get is 1.6. So that is 1 gauge thicker. And you look at in a list, in the manual, later will show you what is the list of available. So we need to use the available material, otherwise you have to procure the special material with special thickness, then it will be expensive, take too long. We don't have much time, so we just need to work what we have. Okay, remember two principles, same material, 1 gauge thicker. Always think of that. However, we cannot just let it loose. We have to do the check. That's why analysis has to be done. Analysis for repair require the following check: tension check, net tension failure, shear check, shear out, shear failure, compression check, bearing. Check to ensure fasteners are able to transfer the load, the applied load. Also, you need to check whether you use appropriate fastener or not. Okay, that is analysis to be done. Maybe 2 minutes. Okay, let's continue. Okay, now what is next? Okay, how do we do it? For the reverse engineering approach, structure engineer, you are structure engineer. Okay, so what you apply for, if you talk to Airbus, you apply for structure engineer. Must calculate allowable load in the pre-damage state. Calculate allowable load in the pre-damage state. And then compare to the post-repair allowable load. Allowable load, not limit load. Allowable load, maximum load. And then you compare allowable load before damage, and then allowable load when you already have installed the doubler. Okay. So you can calculate the load only if the stress in the repair is assumed. So how to assume it? How to assume the stress? You must know the material. And then the material, you go to the table and then you determine what is the stress for that kind of material, for the thickness, for that material, for the direction of the grain of the material, and then for the major structure, secondary structure, primary structure, secondary structure. Then you have to determine, you have to select what is the most suitable stresses. That stress we use to calculate to the stress, you time the cross-sectional area of the damage, then you will get load. So that's a load, that loss. And also you also can calculate the stress of the material. You make the doubler, time the cross-sectional, which is the thickness of the doubler, and then that is the load that the doubler can take. So the load of the doubler over load of the repair of the original, and then you will get the margin of safety factor. Sorry, what do you get? You got 3 items I was discussing with you. You will get reserve factor. Sorry. And then reserve factor should be more than 1. Okay, clear? Okay, let's go detail later. That we go browse through this. Okay. So check. So this equation given how to calculate cross-sectional area over the stress. I will explain to you later on the FTU or 1.5 times FTY. However, what I'm trying to say to you, for the load, you have to multiply cross-sectional area with the stress of the material. So it's given here. And then from there, you calculate the reserve factor. Okay. And then next, you determine the number of fastener. Okay. So number of fastener here, the stress, the load maximum on the original divided by the number of the force of the strength of the fastener, and then you will get the number of fastener. For example, if you are your original skin loss is say 100 Newton, then you choose a fastener of 50 Newton each. So 100 divided by 50, you got 2. You need 2 fastener to transfer the load each side. So 3 things. Calculate the load, calculate reserve factor, determine the fastener row, and then determine the maximum shear for the fastener, and then reserve factor again, number of fastener based on shear, and then you calculate the either is single shear, double shear. So that is you need to consider how many layers of doubler that you put in. And then you check bearing stress. Okay, after you check the bearing stress, and then you may want to look at also the crippling, buckling, continue on. Then there are 11 of this example of repair. For this case, you have defect this horizontal flange, cut it off, put a failure, put a double, and then the process takes place here. You need to calculate the load on the original, load on the doubler, and then you calculate laser factor, and then you calculate the number of fastener, and you calculate the bearing. So you have to do the shear out, net tension failure. So those are standard check. We will go through detail later. But I just try to go and walk through the manual. That's what you get. So we have 11 of this. So for your repair proposal, you may want to see any of these 11. You can choose one of it as your concept repair for the assignment. But most of the time, your assignment for the skin will be using either 11 or 10 or 11. Example number 10 or 11, because example 10 11 talk about skin. And most of it will be from 1 to 10 because those are angles. So you have to use appropriate angle repair. Any questions so far? No? Next one. There's another manual. They are associated to that. We have 51. Are you seeing my page?
Yes, sir.
Yes, sir. Yes, sir.
So this 51, sorry, 51, 70, 10. Okay, sorry, this old one. We have next one is 51, 11. 51, 70, 11. Okay, so this is technical data for reverse engineering method. Remember, our repair method is reverse engineering method. Why reverse? Because we do not have the load on the structure. We calculate the load by assuming the damage of the area will be the load that you need to use in design detail of the repair. Okay, this is material allowable value, technical data for reverse engineering, material allowable value. So this material allowable, you can see same symbol come again. So you go back to your mechanics of material, try to understand all these symbols. And most importantly, also the list out the material, the start, sheet, plate, cap, extruded sheet, crack, so 2024, 7075, tempering, extruded 7075, 7175. And then the sheet metal, if you need to have thinner repair, the repair too thick, you want to make it thinner, so you use steel AISI 301, but you have to treat the stainless steel with cadmium plate, so you will not get corrosion due to the contact with aluminium. So now what you need to understand here, this table give you this manual give you a table. This table here is where you select your material strength. Okay. You can see there are many tables. I'm showing you 20243. So look at temper T3. If you want to work on 20243 sheet metal, and your thickness say 1 mm, so it should be between 0.25 to 1.6. And then you need to choose this value here is megapascal. So this is tensile ultimate. Also you get tensile yield, you also get compression yield, shear ultimate, bearing ultimate, shear ultimate, bearing yield. So all given here. So what is our interest here, what I want to show you, there's two things here. There are box here. 435, 440, 405, 415. Which one you choose? To choose, if the repair is small and the weight is not significant, we use the worst one, 405. So we just become very conservative. We can say that the strength of the material that you want to put as a doubler is only 405. Not an issue if the repair is small. There was not a weight, was not a main issue, because 405 you need a thicker part. If you use 440, then you will use less. Okay, when 440 is stronger than 445. That is the reason why. However, you need to understand what's A and B. For A, when they did the test, say we have 100 coupon, 99 coupon will give the value 435. Mean 99 coupon failed at 435. Whereas 90 coupon failed at 440. So 435 is more confident because 99% result with 435. So that's the reason. That is the explanation of A and B. For A is more probability of the number value here 435 highest, and 90% 440. Why we need these two? If your repair is big, weight is a concern to you, and also then you have to classify either structure secondary or primary. For secondary, you may opt for the 440. So you're not gonna have very thick, heavy secondary structure. After all, it's just secondary structure. For L and LT, that is the Regrain direction. As you make any part, extrusion, plate, whatever, you have to go through some process. In that process, in plate, in extrusion, and skin, they have grain. They establish grain. So grain is a direction, just like you go see wood. Wood, you can see wood grain. So the behavior of material like that. So it's grain. So the L is longitudinal. The grain going to direction. Horizontal here. If you have plate, you roll open. You roll open, and then you can see along that roll open, along the roll, there is L. But any transverse across the roll will be longitudinal transverse. So along the roll you pull, the strength is higher because it's pulled along the grain potential. But when you go for longitudinal transverse, you pull sideways is less. That's why you can see longitudinal 435, longitudinal transverse is 405. It easily fail if you pull it not in direction of the longitudinal grain. So most of the time, for me, my practice is for small repair, which is not significant for the weight. I always use the most conservative one is 405. This is the load that we use to multiply the cross-sectional area of the defect, and that's how we establish the original loads that go through the parts. Similarly, if you are use this as a doubler, it's a load you multiply to the thickness of the doubler, and then you will get what is the doubler capability. So the doubler capability, load capability divided by the original load, then you got your reserve factor. Any questions so far? Okay, it's a lot more material here. In fact, up to the stainless steel, they have given the information. Okay, next I will show you still on the technical data for reverse engineering methods, fastener. And here we'll give you all the detail about fastener load, fastener strength capability. Okay, for example, this table here, MS 20470 2043, that's material. This is a fastener. MS 20470 is most commonly used rivets. Okay, MS 20470 solid rivet universal head. Okay, in sheet 2024 clad for bear. So for the rivet in the 2024 sheet, then this is strength for AD, DD, KE. I think you learn already what is AD, what is DD. Is the rivet type with the material 2117 is AD, 2024 is DD. So for this, you can see for each thickness, that is the strength that for the rivets. So 4mm rivets. If you're talking about AD rivets, if you are working on 1.4 mm thick material, you'll consider load only 2680. Okay. And if you're working on 1.8 very thin material, you only consider 2460. You go higher than this, the skin already fail. So it's not actual shear strength of the rivet, it's a failure of the joint, the failure of the skin. The actual strength is 2680. For this sample here is DD, actual rivet shear is 3660, it's maximum single shear. Okay, this is the load that we use for the material with respective material thickness. You can see the 2117 for diameter, you go to 1.5, it no longer. You cannot use this AD 2117 4mm into 1.6 mm, because if you use that, the rivet will fail, no longer shear. It will also have some form of bending, so we don't use that. We cannot use in very thick, we cannot use in very thin. For example, here 4mm, we cannot use in 1.8 mm, very thin. It will just fail the material. So next is the manual technical data for river engineering, allowable, local buckling, load for standard section. So here we calculate buckling and crippling. I will go through that later. How we want to make sure that repair that you introduce is not fail in buckling and crippling. So this analysis here of 511714 will give you the detailed analysis of the buckling. And then we have another repair general guideline. Okay, there's only 4. So we will work on the 511710, 5111, 517011, 517013, 517014.